So in this video what I'd like to do is introduce you to the idea of porosity and see how it can help us relate Darcy velocity to our fluid velocity, so the actual velocity of the particles that are flowing through a porous medium. So I think most people are reasonably familiar with the idea of porosity. If you zoom in on this sandstone right here that I've drawn, you would find that it's composed of, lots of little rock grains, these little sediments that are packed together. So these little sand grains are packed together. But no matter how hard you try to pack them together, you're always going to have some void space, so this black space in between the white. You're going to have this void space or pore space. And sometimes it's occupied by fluids, sometimes it's occupied by just air, sometimes it's void. I guess hypothetically it could be void. But the point is that there's always space in a rock that is not occupied by sediment. It's just free space essentially. So we describe this with the term porosity, and we designate it, or we denote it, with the symbol phi. And phi is equal to the ratio of this, I guess if you were to take all the contributions of this black void area within our rock and you add it all up, we call that the pore volume. So V sub P, and then you divide that by the bulk volume, which in this case would just be, if you take the height, the length, and the width of this rectangular prism, that would be the bulk volume of this rock. So I'll write that as V sub B. This is the definition for porosity, or perhaps it's a definition. I think there's others, but for now this is sufficient for us. So what I want to think about is, in the context of the last video when we talked about Darcy velocity, and we've talked about this actual fluid velocity, how fast the water molecules would be traveling through a rock. With that in mind, think about how porosity enters this mix. So let's say we have some fluid that's flowing through here, and say with a volumetric flow rate Q. So I could, if I say that this cross-sectional area here, this would be the bulk cross-sectional area that I'm drawing here, or that I'm shading in. And it's bulk because in reality, if you zoom in on it like I have, only some of this red area is actually open space that is available for flow. So AB is not the true area of all the little conduits. It is over representing how much area we have to flow through. So how can we relate the bulk area to the actual pore area, the actual space? Well, if you just kind of look at a thin slab of rock here, if I were to make a cut here, and this cut would have, if I look at it straight on, and so this is our rectangular cross-section. So essentially what I drew here, so not too much different, but we're going to have these pore spaces, and I'm blowing them up. I'm making them much larger than they actually are, but it looks something like this Swiss cheese gaps here. And this entire area, if this is H, and maybe we call this L, or let's call it W actually, this is going to equate to the bulk area, but we just want we just want to count this right here, or we want to see how this relates to the bulk area. And so using the porosity definition, what we could do is we could say, okay, well, if we were to kind of take the depth out of this equation, or divide through by whatever depth this has, so kind of popping into the screen, then this relationship would suggest that we have our bulk area, so AB in the denominator, and then the numerator we would have the pore area, so I'll write that in blue, so that would be A sub P, our pore area. And so we can say, okay, A sub P is going to be equal to the product of phi, our porosity, or phi if you like to pronounce it that way, times our bulk area. So now let's go back and look at our definitions for Darcy velocity and our definition for I guess the original velocity, the true velocity that we had. So originally we said u, our Darcy velocity, is equal to q over a sub b. So u equals, let me write that neater, u equals q divided by a sub b, q divided by a sub b. Let me keep those colors consistent. Okay, and we also said previously that v is equal to q over a, where a is the actual area available to flow, so that would be the same thing as a sub p in this case. So we'll say that v is equal to q divided by a sub p. A sub p. So if we want to get a relationship strictly between u, v, and phi, we just have to eliminate q and the area terms from this equation. So how can we do that? Let's see. Okay, well, first of all, we can relate a sub b to phi and ap, so we can write, I'm just going to write in one color because I think the colors are maybe taking up too much time at this point. So we can write that u is going to be equal to q divided by a sub b would be the same thing as a sub p divided by phi. So that would be the same thing as multiplying by phi and dividing by a sub p. So hopefully that was clear. I'm basically solving for a sub b explicitly, which is a sub p divided by phi. Then when you divide by that, you're essentially taking the reciprocal and multiplying by that. And now we can solve for q here. So can't help but use some different colors here. So q equals v times a sub p. And if we substitute q for this q right here, we do that in that same color. If we make this substitution for q, then we will have u equals v times a sub p, so v times a sub p times phi divided by a sub p. And the a sub p's cancel, and so we're just left with u, the Darcy velocity, is equal to, and I've kind of been dancing around the term, but there is an actual term for it. It's called the interstitial velocity. That's the velocity of the actual fluid, if you were to, I don't know, measure it with a stopwatch and see how far it goes in a given time interval, multiplied by the porosity. And it's important to note that this is really only an approximate relationship, because we did make some assumptions about the geometry and made some simplifications, but this is a pretty good relationship that relates our Darcy velocity to our interstitial velocity, and porosity is how we make that connection. So I still haven't really shown you the motivation, but I think we're getting closer for why we want to use this U term. And I can kind of touch on it right here, is that we don't always know what the true pore area, or the area available to flow, is going to be, and sometimes we don't want to think about it. We just want to think about bulk areas, because those are easy to deal with geometrically. So if you were dealing with the lateral surface area of a cylindrical geometry, for example, you would just want to think about that and multiply it by a flux, and you would get the actual flow rate. So anyways, I'll talk about that more in future videos, but hopefully this gives you some kind of sense of a relationship between this flow rate divided by bulk area versus this flow rate divided by area available to flow, and how porosity is that connection. I'll see you soon.